Let's look at two real-world problems. It's a likely bet that a problem like this might be on the AP test. It usually is. And if you notice, this one happened to be an AP problem from the AB test. A test plane flies in a straight line with a positive velocity in miles per minute at time t minutes, where v is a differentiable function of t. Right? So that's saying that v is the derivative. Selected values of v of t for t between 0 and 40 minutes are shown in the table above. All right, so now something very important to note is that the total distance equals the change in x times the height of the velocity, right? And that's the Riemann sum. So we're going to use we have the directions right here. This was literally taken off of an AP test. Use a midpoint Riemann sum with 4 subintervals of equal length and values from the table to approximate the. Now this is something we're going to be learning, but I will tell you that that elongated S stands for sum, right? And we're going to learn a lot more about that. But that elongated S stands for sum. So it's telling us to sum up all of the rectangles from 0 to 40. And it's telling us that v of t is the derivative. And when we sum up all of the values for the derivative, we are finding the total distance in this case, because the derivative is velocity. All right, so now let's do our midpoint Riemann sum. Let's find our change in x. So change in x is, and we know they're equal lengths, right? So that's why I can have one change in x, right? Because it says 4 subintervals of equal length. So 40 minus 0, there are, let's find out how many subintervals we're going to have. All right, so I need to make sure, all right, I got a value in the middle. Got a value in the middle, got a value in the middle, a value in the middle, right? Actually, we knew how many subintervals. I'm sorry, it says 4 subintervals. But now we can see 1, 2, 3, 4 subintervals. So the change in x is going to be 10. We've got our change in x. We can find our values now. The midpoint Riemann sum is going to use the value in the middle, right? So this is the value for the first bar, second bar, third bar, fourth bar. Okay, right? So and this is, by the way, called integral. The integral, and we're going to learn a lot more of that about this. But just think of it now as a big elongated S for summing up all the rectangles. From 0 to 4, v of t dt is equal to the area under the velocity curve. So make sure, by the way, you're filling in your notes, because this is a key idea. Oops. I don't know what happened to my v there. Which equals total distance traveled. All right, so let's find the total distance here. Switch colors. I'm seeing too much red. All right, so this, the integral from 0 to 40 v of t dt. We're doing a midpoint Riemann sum. So we have our change in x, which is 10, times the heights of the rectangles, which is 9.2 plus 7 plus 2.4 plus 4.3, which would be 10 times 22.9, which is equal to 229. Now, let's put units on that. That's 229 miles. All right, so now we have done question 1. Now we've done the computations that lead to our answer, That's the computations that lead to our answer. Number 2, using correct units, explain the meaning of the integral of 0 to 40 v of t dt in terms of the plane's flight. I'd be surprised, highly surprised, if there wasn't a question just like this on the AP test. So now let's do, this was 1, now let's do 2. And really 2 is very easy. It's just explaining what this is. All right, so this, we can do this in one sentence. The plane, so we're talking about a plane here. The plane traveled 229 miles in 40 minutes. And that's all there is to it, right? It's just explaining with the correct units, right? So this, when we take the area under the velocity curve, its distance, how much distance? In this case, it was 229 miles. How long did it take? 40 minutes. That's all there is to that, all right? Let's do one more. And here's the next one. There we go. All right, so if there is initially 1,000 gallons in the tank at noon, approximate how much there is in the tank at 1 o'clock. All right, so make sure you interpret your units correctly here. We're going from noon to 1. Well, how long is that? Well, that's 60 minutes. And we don't want to call that an hour, right? We want to call that 60 minutes because the units is in minutes. All right, so we're going to calculate the, if we want to calculate how much is in something, right, the total, that's going to be equal to the starting balance, the starting amount, plus the amount added. We know the starting amount. It says there's initially 1,000 gallons. That's the starting amount. To find the amount added, we're going to do it twice. You usually will do this once, right? But this is our practice, so we're going to do it twice. So we're going to do a left-hand sum and a right-hand sum, right? So for the left-hand sum, now look carefully. Do we have a constant change in the values? Yes, right? We're going, each one of those goes up by 20, right? So we can just do a change in x. We don't have to, and then take the heights and multiply by the change in x once. We don't have to find the area of every rectangle. So I always look to see, okay, is it a constant change in x? Yes, those are going up by 20s. So the change in x, and we're going to do this. We have 1 bar, 2 bars, 3 bars, right? 3 bars there. So change in x is going to be 60 minus 0 divided by 3, which is 20, which makes sense, right? Because those numbers are going up by 20s. And it'll be the same whether it was a left-hand Riemann sum or it was a right-hand Riemann sum. All right, so now let's find the change in the volume. All right, so left-hand Riemann sum, right, is going to be the 20 is our change in x, times the heights. And if we're doing a left, it's going to use the values on the left-hand side of the bar. So there's for the first bar, the second bar, the third bar. So 5 plus 16 plus 32, which would be 20 times 53, which is going to be 1,060. I'll put it over here. Right. 106, and yeah. All right, the right-hand Riemann sum. All right, so the right-hand Riemann sum doesn't use those values. It uses the values on the right-hand side of the bar, right? So it's going to use the 16, 32, and 30, right? So we'll add those up, right? And so 60 would be 48, 78, right? So 20 times 78 is going to be 1,560. We should probably put units on that. That's gallons. Gallons. All right, if you got a real world problem, put units on it. You usually get a point for just putting the right units on it, even if your answer was totally wrong. All right, so now let's end this question by finding the total amount. So if it's the left-hand sum that we're using, the total is the starting amount, which is 1,000 gallons. The amount added, if we use the left-hand sum, is 1,060 gallons. So that means it is 2,060 gallons. The right-hand sum would be 1,000 plus 1,560 for 2,560 gallons. Let's interpret this, right? So the amount, does it say what this is? Of something's, it's hot water. The amount of liquid. We know it's a liquid. Only liquids are measured in gallons. There we go. Now we're spelling liquid right. The amount of liquid in the tank after, and you can say after 1 hour, after 60 minutes, at 1 o'clock. Okay, we'll put at 1 o'clock, since the question says at 1 o'clock. At 1 o'clock is, I'm going to put approximately, because we know this is an approximation. We got two different answers here even. Is approximately, and it's not a bad idea to put approximately for the Riemann sums, approximately 2,060 gallons. And I'm going to put in parentheses using a left hand Riemann sum. I need a little bit more space. That's probably more space than I need. That's way more space than I need, but that's all right. And because you can always rewind to see the stuff above, but you probably have that written down. I don't even think there's anything above that. And yeah, that's just I need that actually. I'm sorry, that's not a period. That's just a for abbreviating. And approximately 2,560 gallons using a right-hand Riemann sum. And so just to review, increasing, decreasing, and overestimating, underestimating. Actually, let me finish writing what I'm saying because I'm forgetting what I'm saying. Right-hand Riemann sum. So let's talk about which ones, and so first of all, that's all there is to, I like Riemann sums, to interpreting a Riemann sum. If you understand them, they're very, very straightforward. The computation's not too difficult, and all your units are there, the setup is there. You just have to be able to go about solving the problem correctly. Right? So here the amount of liquid in the tank at 1 o'clock is approximately 2,060 gallons using a left-hand Riemann sum, and approximately 2,560 gallons using a right-hand Riemann sum. Now, which one's an overestimate and which one's an underestimate, and why? All right, so you might have figured out that the left-hand sum is an underestimate and the right-hand sum is an overestimate, but why? It's an increasing function, right? So if it's an increasing function, I'm going to just put that in there to remind you. Because they might put this, and they might ask you, is this which one, is it overestimate or underestimate? They probably won't have you do a left hand and a right hand, but they may ask you, maybe they have you do a left hand and ask you, is it an underestimate or an overestimate? And you should be able to say that actually, let me make this a sentence. The left hand, I'm going to abbreviate Riemann sum. Don't abbreviate Riemann sum on a test, but I'm going to abbreviate Riemann sum here. Left hand Riemann sum underestimates and right hand Riemann sum. Although actually, yeah, you put left hand and RS. What else could it be but Riemann sum? Let's face it. And right hand Riemann sum overestimates for an increasing function. So a little review there. And in the last video I went over that because I don't think I was 100% clear, right? Because it the concave down, concave up, concave down part was just kind of a coincidence. But what really matters is it increasing or decreasing. Because let's think about it. If the function's increasing and we're using the lower values on the left-hand side, well, of course it's going to be an underestimate. And if it's increasing and we're using the upper values on the right-hand side, well, of course it's going to be an overestimate. Right? So one last thing, though, before I end this tape. One slide. I have one more of these problems, but I'm saving it for another video. So far we have 3 ways of estimating an integral using a Riemann sum. The left-hand rule uses the left endpoints of each subinterval. The right-hand rule uses the right endpoint of each subinterval. The midpoint rule uses the midpoint of each subinterval. Right? So if f is increasing on AB, then the left is the underestimate and the right is the overestimate, and the actual value, the actual area under the curve, so this right here, this is referring to the actual area under the curve. And we're going to learn all about that notation, actual area under curve is going to be between them, because the left-hand side will be an underestimate and the right will be the overestimate. If f is decreasing on the interval, then the right-hand side is an underestimate and the left-hand side is the overestimate, and then the area under the curve, the actual area under the curve, is in between those two. But we have not learned every possible way that we could sum up using an approximation. We've used a left-hand rule, a right-hand rule, a midpoint rule. We have one more coming up, and that's going to be in the next video, and that is the trapezoid rule. Yay! Yay for trapezoids. All right, so we're going to learn about this one in the next video. So come join me now that we've reviewed these with some really important real-world interpretation problems. Bye for now.